Ladies and gents, welcome to this week's Geotalk, brought to you on Zoom Live, Zoom webinar format this time. We're trying out the Zoom webinar format, and so you'll see the most differences when we come to the Q&A at the end of the webinar. And I'll mention how we deal with questions at the end. But today we welcome Professor Bertus Smith to the Geotalk stage. Bertus is well known to the Geotalk stage and is an associate professor in the Department of Geology at the University of Johannesburg, where he got both his MSc and his PhD on very diverse topics. His PhD focused on geometallurgy of the Merensky Reef and the applications thereof, whilst his MSc, which is much more along the lines of tonight's talk, focused on Meso-Archean iron formations of the Wits and Pongola supergroups and their paleo-environmental implications. And of course, his research interests are as diverse as those two different thesis topics. And really, he's interested in understanding and characterizing the genesis of high-grade iron ore deposits, as well as chemical sedimentary rocks from the Archean. And of course, he's still involved in various geometallurgical applications. So, Bertus, thank you so much for joining us, and thank you to John Hancock's and CCIC Group for sponsoring these Geotalks. And we have roughly 20 people in the audience, I think, and a whole bunch of people watching on Facebook Live as well. So I'm going to stop sharing, Bertus, and you can share your screen and unmute.
Okay, Grant, thank you very much. So let's get this going. Hopefully everybody can see the blank screen, and now hopefully you can see my presentation. Thank you for the privilege of giving a talk at Wits Geotalk. I've done it once or twice before, and it's always a pleasure and a privilege. So I'm very happy to be here. So welcome everybody to my man cave here at home. You know, it's very convenient being able to present across the world from the convenience of your own little at-home office. I did see, however, when Grant was busy introducing my research interests, the participant numbers just dipped by 1 or 2. So yeah, I hope that's no indication of of what's going to happen later on. But anyway, so here's my talk. It's a bit more broad interest, still specialized in some ways, but it tries to have a more broader, holistic view of South Africa's geological record, especially with regards to evidence for early life. So I'm going to start at the beginning and sort of work my way towards the end and tell you of some interesting case studies, interesting field sites. Hopefully there'll be some pictures that all of you think is quite nice pictures. I think they're nice pictures, but hopefully you'll agree with that. And yeah, hopefully places, once we are able to move around more freely, you'll be encouraged to go and visit these amazing geological sites. So, so I'm going to basically focus on the Archean and the Paleoproterozoic chemical sedimentary rocks. I will talk a little bit about the Neoproterozoic as well. But I'm basically going to say, what do we see in South Africa's early Earth geological record that might indicate signs of life? So let's get going. So as we know, the geological record is actually Earth's biography, and there's just so much we can see, you know, in the history of the Earth. You know, a lot of better techniques, especially geochronology, has enabled us to really place these things into different time brackets and construct what we see as the geological time scale. So the Earth is 4.56 billion years old, and there's approximately 4 billion years of geological record to look at, unless you count the Jacks Hill zircons, which will then put it at maybe 4.26 billion years of geological record. But I mean, as we said, it not only records processes of what has happened below the surface, but also at the surface, and that's where my research interests lie. So therefore, if there was life at the surface of the Earth, maybe that life left behind some sort of evidence that it was around. So actually, from about 542 million years ago till today, it's very obvious, abundant evidence of life in fossils and trace fossils as well, because we had the Cambrian explosion of life. So then eukaryotes, complex organisms, really started to take over and build up these different food chains. A lot of them died, and they got preserved, you know, imprints of that got preserved in the geological rock record. But my big interest has to do with what about before that? What do we do to try and look for life before the Cambrian explosion of life? So again, as we say, two main types of life we get, prokaryotes and eukaryotes. Prokaryotes, single cell, very simple, bacteria, archaea. And then we get eukaryotes, cells with a nucleus and a membrane. We are, for example, eukaryotes. So eukaryotes are very good at leaving fossils behind. There's a picture I took in the Frankfurt Museum of Natural History. But as always, I always have a few gripes, with Hollywood. And for example, there's the T-Rex on the left, there's the T-Rex on the movie poster Jurassic Park on the right. And I know this is a common running comment, but I'd just like to reiterate it. Seriously, they could have put a Stegosaurus on there. It would have been more accurate. Otherwise, they should have called it Cretaceous Park. But I guess it's not as catchy from an advertising point of view. So only these complex organisms leave behind these clear evidence for life. But what about the early Earth? How do we look for evidence of past life when it comes to prokaryotic life? Now, you can be lucky sometimes, and bacteria, especially cherts, can leave behind fossils. But the issue there is they're very small. They can be very hard to find. And even when you find them, they can be very controversial. There are people that have built their careers on writing papers, shooting down what other people consider evidence for fossil bacteria. So it can sometimes be dubious, sometimes a bit more clear-cut, but it does get quite controversial, lots of debates around it. There, a picture from the beautiful McCarthy and Rubich textbook showing what people consider to be fossilized bacteria, most likely in a chert. Other morphological evidence we see, some of this is a bit more clear-cut. You can really see it nicely in the rock, in hand specimens, even at outcrop scale. Things like algal mats and stromatolites. Those are also other ways we can try and look for evidence of early life on Earth, predating eukaryotic life. And then also geochemists also try and look for evidence of early life by looking for indirect geochemical evidence, things like organic carbon, certain isotopes, some fractionations only, while generally or more commonly occur when life interacted with the rock forming process, and then also looking for biomarkers as well. There's an example of measuring the carbon isotopes and carbonates, and quite often when you see a depletion in your heavy carbon-13, you start looking, it starts looking like it could be evidence for organic carbon having been in the system. So a quick interlude to introduce certain terms. Most of you probably already know this, but I did make up this talk for a broader audience. So we start with stromatolites. They are biochemical accretionary structures. They're these layered mounds. They can be column-shaped, sheet-like, but essentially occur in sedimentary rocks, most commonly in carbonates, limestones and dollostones. And essentially they form by the growth of layers of bacteria. So you get bacteria growing in fairly shallow water where there's enough sunlight penetrating into the water to enable their living processes. And essentially what happens is they form these mucus-like layers, and either a little bit of detritus will get caught up in that mucus, or you precipitate directly out of the water, a mineral precipitates onto that mucus, and then the stromatolites will slowly but surely grow through those mucus-like layers. And their morphology and size can give some indication as to water depth in which they grew as well, but I'll get back to that later. Then another rock type I want to introduce, most people generally know this. This is my favorite rock on Earth. I absolutely love these iron formations, especially the banded iron formations. There you can see a very nice picture from Helpmekaar College of the Contorted Bed that runs east to west across Johannesburg. And both Wits University and University of Johannesburg is built on the geological unit that contains this iron formation. They are chemical sedimentary rocks, meaning they precipitate from a solution, usually marine water, and they contain enormously high iron content. Usually the bulk of the rest of the rock is made up of silica. So it's mostly iron-rich minerals and chert making up these rocks. but they do come in early Earth studies quite importantly. Firstly, when we look at a lot of the geochemistry, they do appear to be paleoproxies for ocean water chemistry. So most geochemists think they're pretty accurate archives for changes in marine chemistry. But not just that, there's a very good chance that a lot of these iron formations were formed by bacteria. Because if you look at iron oxidizing bacteria, if you're sitting in an environment that's fairly low in oxygen to oxygen free, and there's a lot of ferrous iron around, bacteria will love that. And what they do is they precipitate ferric oxyhydroxide as a byproduct of their metabolism. And in theory, that should precipitate what ends up being a banded iron formation. So quite a lot of work goes into that as well. So now we start with South Africa and its geology. More than 3.5 billion years of geology is preserved here in Southern Africa, and it's better preserved than in a lot of other places in the world. This is really a very nice place to look at early Earth geology. Relatively low metamorphic grades, a lot of good preserved geology. Mining companies have been putting a lot of deep level drill cores into early Earth sedimentary units, looking for gold, looking for iron ore. And I'm now going to run through quite a few of these places where you see direct or indirect evidence for life. So this is really a fantastic place to do paleo-environmental reconstructions, especially for the Archean and the Paleoproterozoic. And of course, it's a big country, but it's not that big. For example, a lot easier to get from Johannesburg to Kuruman than it is to get from Perth to the Brockman Iron Formation in Western Australia. So it's a really nice place to do early Earth studies. And these are all the different places. So we're now going to start an Archean Paleoproterozoic adventure. So essentially, to get back to this poster, this talk is essentially going to be Archean Paleoproterozoic Park. And instead of a T-Rex fossil, there's some bacteria up there. So let's start this journey. So as always, introducing the Hadean, first year's Geology 101. You talk about that first, say, 500 to 600 million years of the Earth's history. Every now and then they sort of readjust the end of the Hadean. I know when I was a first year, they put it at 3.8 billion years, but now they've shifted it back to about 4.1. And of course, we think this must be hell on earth because there's so little preserved geology, whereas most geochemists are pretty sure the Earth is 4.56 billion years old. So magma ocean, meteorite bombardment, toxic atmosphere. But you see in the Jaxial zircons, it's strongly implied that there was some water at the surface, at least at about 4.2, 4.3 billion years ago to form some of these minerals. But was there life? Well, that's very hard to prove. It's very hard to say. I would say the oldest indirect life on Earth, and it's really indirect, is in the Isua Greenstone belt, which is about 3.8 billion years old. But we're not talking about Greenland. We're talking about South Africa. So where do we start? I mean, truly one of the crown jewels of South African geology, the Barberton Greenstone belt. What a fantastic place, beautiful area, World Heritage Site now. And just a fantastic place to do geology. But please note, always pack a rain jacket. The weather changes there quite quickly. And doesn't matter which time of year I've been there, I've always caught rain while being out in the field. So really a place to pack a rain jacket when you do field work. And geologists have absolutely scrambled to study this. I mean, there's geochemists and other geologists that spent their entire lives working in the US, but they built their entire scientific career publishing on the Barberton Greenstone belt. Things like primitive crustal processes, primitive lava flows, early oceans and tidal environments, early meteorite impacts, and of course, topic of this talk, evidence for early life. So we'll quickly touch upon a bit of this. So the 3.5 billion year old Onverwacht group, as researchers found what they think are microscopic bacterial fossils, and those are the pictures there to the bottom left. Once again, I must say, especially that top picture, when you look at that little filament there, that to me looks pretty convincing, but other people might debate against that. It is very tough. Bacterial fossils can be quite dubious, a big gray area at times. But luckily, if you just move up into the next group, the slightly younger fig tree group, 3.3 billion years old, there we see stromatolites. And they're pretty convincing stromatolites. I would say the one on the right is a bit more convincing than the one on the left. But we are pretty sure these structures were formed by bacteria living in shallow water, growing these mounds. Then again, if you go up above the fig tree group into the Moody's group, which is now about 3.2 billion years old, there you get some pretty convincing algal mat structures in sandstones. So if you look there at the bottom, that's present-day Tunisia. If you look there, you get these algal mats growing on certain beach environments. You look at the top, that's from the Moody's group sandstones. These pictures from a publication, the one on the right, I took in the field myself. Very interesting that it looks like 3.2 billion years ago in the Barberton Greenstone belt, you had this very similar process, a similar bacteria growing in a shallow beach environment as we see still happening in some environments today. Quite nice to look at, also fairly easy outcrops to get to. There we go again, my favorite rock, the BIFs, banded iron formations. So both the fig tree group and the Moody's group contain banded iron formations. Bottom left, you see a very nice outcrop from the fig tree, and the bottom right, you see one from the Moody's group, which I took myself in the field. And, you know, it looks like there was a strong chance that at 3.3 billion years ago already in South Africa, in a sea or ocean, you had iron oxidizing bacteria doing its thing. So, yeah, these BIFs kick in pretty early in South Africa's geological record. Now we move from the more Paleoarchean into the sort of Mesoarchean, the Middle Archean, the Pongola and Witwatersrand supergroups. I'm going to spend a little bit more time here, as this is one of my personal research interests. So here again, South Africa is such a nice place to work because essentially South Africa had geologically settled at an earlier age than a lot of other places on Earth, namely the Transvaal craton, which essentially by 3 billion years ago was mostly stabilized. This was a time on Earth. There's one or two other cratons like the Slave craton in Canada that also stabilized early, but most other cratons only really started stabilizing closer to 2.6, 2.5 billion years ago. So what's very nice is you get these beautifully preserved marine and terrestrial sedimentary successions that essentially were deposited on passive marine margins, alluvial fans, fluvial environments. So again, from a sedimentological point of view, you're looking at things forming in South Africa at that time that probably were not being formed in other places, or because of structural instability was being deformed or destroyed all the time. So really, from about 3 billion years ago, you're really in business when you work in South Africa. So we'll start here with the Pongola supergroup, and specifically the lower part of it, which is the Nsuzi group. And here you're essentially looking at the oldest supracrustal successions in the world. In the Nsuzi group, it's still a bit unstable. It's more lava than sandstone, but still things were really starting to get stable. And here you get your oldest stable continent morphological evidence for life. And this is sitting at the Witwatersrand inlier. And you get these beautiful stromatolites right there, and you see them in other parts of the, other outcrops of the Nsuzi as well. Like, for example, at the Buffalo and Mazibeku River sections, you can also find these stromatolites. But to me, they're quite at their most spectacular in the Witwatersrand. You'll see as well, there's quite a bit of chert, and the chert has really preserved the structures as weathering started taking place. And there on the right, there at the bottom with the scale ruler, that's not a boot mark, that is that's a ripple mark. So a fantastic section with, changing hydrodynamic conditions from water flow doing this, water flow doing that. You can even see little chert layers that got churned up by storm wave action. It's absolutely a beautiful outcrop. But I do want to make a point. I hope Grant is okay with this. This is basically on the Matatane River Lodge property. And at the moment, Matatane is trying to introduce the Big Five on their property, and they're putting up a big game fence, and they've sent this out, and essentially that big game fence is going to close off all this geology to people trying to do field work there. Essentially, if you want to look at it, you have to take a game ranger with you. So watch the space. Maybe we can do something about this, because this White-Mfolozi River section is such an important part of South Africa's geological heritage, and it really would be a shame to have it basically closed off. But it's always that difficult thing, you know, with tourism. You know, people want to make a living and they want to make some money. So now we move up out of the Nsuzi group and we go to the Upper Pongola supergroup, which is the Muzan group. And for me, this is where the fun starts. This is really the oldest stable continent iron formations in the world. So what we're looking at there, that's also on this White-Mfolozi River section. That is very close to the base of the Muzan. It's beautifully exposed and preserved there in the White-Mfolozi River. And what I'm standing on there is the Vlakhoek Member, or the Azer Main Iron Formation. This is, from what I know, in the Earth's geological record, that is the oldest, what we call superior type iron formation. Greenstone belts have what we call Algoma type iron formations. They show close stratigraphic association with volcaniclastic deposits, lava flows, very unstable tectonic conditions. But the superior type iron formations, they form part of broader sea level changes in marine successions. So you're typically seeing them capping maximum points of transgression, nicely associated with sandstones, shales, carbonates. They really form on what we think are passive marine depositional, passive margins, or maybe sometimes back arc basins, but they're essentially part of very nice, stable marine sedimentary successions. So this one over here is an interesting one. There have been now about 3 or 4 publications on this unit over the last 6 years or so. So very interesting stuff happening there. And this is also unique because if you go to iron formations in the from anything older than about 2.45 billion years, iron formations actually contain very little manganese, which is quite surprising because if you look at today's Earth, iron and manganese are quite closely associated in the deep ocean in ferromanganese crusts. So back then, it goes with, you know, it's safe to assume that if you're pumping iron into the ocean, there should be some manganese getting pumped in as well. But the manganese does not get preserved in the geological record prior to 2.45 billion years. A lot of people think it has to do with highly reducing conditions, no free oxygen. So manganese is just so easy to keep in solution because it's harder to oxidize than it is to reduce. But this unit and some of the other units in the Muzan group, they are unique because they're actually manganese enriched, and they're about 2.95 billion years old. And that has drawn a lot of attention, especially from geochemists. So let's have a look there. This is a Nature Geoscience paper published by Planovsky et al. Back in 2014. And what he basically did is he did molybdenum isotopes. And he noticed that there's a correlation between molybdenum isotope fractionation and the manganese content. And the best way to explain this is that you had manganese oxidation in the water column, and those manganese oxides actually take this the specific molybdenum isotope signature with it and puts it in the sediment. And the only way to explain that is free oxygen, because interesting thing about iron versus manganese, you can oxidize iron without oxygen. Best way to do it is what we call anoxygenic photoferrotrophic bacteria, meaning they only need sunlight, Fe2+, and they will oxidize that to Fe3+ without needing free oxygen. However, for manganese, so far, the only processes we know of, it needs small amounts of free molecular oxygen to oxidize manganese. There's an exception. Highly sulfidic environments, you can get anoxic manganese oxidation, but these environments were not sulfidic at all. So this was one of these earlier studies implying that at least here in the Muzan group, at the base of the Muzan group, you could have had a free molecular oxygen oasis. at a time when a lot of Earth environments had no free oxygen. This is the molybdenum isotope argument for this. But I'll show you a sedimentological argument for free molecular oxygen in the Muzan group. And here's some beautiful work that has been done by Nick Beekes and Bruce Cairncross and some of their postgraduate students, where they essentially did a basin reconstruction of the Muzan group and the Witwatersrand group of the Wits during the Meso-Archean, showing you exactly what's happening, where it's happening, where the marine basin is getting deeper, where it is shallower. And we were very lucky in the sense that we had access to 2 deep-level drill cores drilled on those little stars you see there, the red star and the gray star. And now if you place that into the broader geology, you'll see there the Nsuzi group, erosional unconformity going into the Muzan. And if you do the basin reconstruction, you'll notice these 2 drill cores. The one is DDN1, which basically sits in the paleo environment where you were closer to the coastline, shallower water, and you get PMH24, which essentially in your paleo-environmental reconstruction sits further away from the coast in deeper water. It's also safe to say that iron and manganese was sourced from the deeper water. There's a lot of geochemical evidence saying it was sourced from hydrothermal processes in the deeper ocean. So essentially, you're bringing your iron and manganese from the deep water towards your coastline. Now, if you now look at the composition of the same iron formation, the Azermain iron formation, in these 2 drill cores, you'll notice that in PMH24, which is in the deeper water, its manganese contents are generally lower. Whereas if you now look at DDN1, which sits closer to the coastline, it's got much higher manganese contents overall. So there's more manganese going into the sediment closer to the coast, whereas further away from the coast, there's less manganese and more iron going into this iron formation. Furthermore, if you look as well, you look at the carbon isotopes, and you see that again in the distal iron formation, it's slightly less depleted in carbon-13. In the shallower ocean, it's a bit more depleted in carbon-13. That also makes sense because your organic carbon input is higher in shallower sediment than it is in deeper sediment as well. So it really fits nice into the broader reconstruction that we know where we are sitting in the sedimentary environment. So we did this reconstruction and we essentially said, well, if you look at the sedimentology, it shows that the iron and manganese contents are an effect of primary chemical sediment deposition. Iron and manganese have different redox behaviors. If you are in an environment and you're pushing up your oxidative potential, your EH, iron will oxidize first and more easily than manganese. You essentially need to start using up the Fe2 plus in your system before you start reverting over to manganese oxidation. And you need manganese oxidation to precipitate it, to rust it out into the sediment. So it makes perfect sense if you look at the paleo-environmental reconstruction that in the deeper water drill core, there's more iron still, whereas if you move into the drill core that had a shallower depositional environment, there's more manganese going into the sediment because you were able to, from a lateral point of view, use up your iron as you move that plume closer to the coastline and you go over into manganese deposition. So from a sedimentary point of view, this supports iron and manganese oxidation. But the implication is if you have manganese oxidation in your water column, you had to have free molecular oxygen. So this is sedimentological evidence that there was free oxygen in this environment. Now we go to the contorted bed, which I spoke about earlier, which sits in the Wits. And here, essentially, we had a look, and again, you look at those carbon isotopes we see in the Muzan, you see the same carbon isotopes in the Wits. There was organic carbon going into these banded iron formations. So there was life in that water column, and most likely iron oxidizing bacteria. But what's interesting about the contorted bed is that if you look at the iron content, you go from a sandstone to a shale to a BIF to a shale back into a sandstone. If you look at the shale above and below this BIF, that shale becomes depleted in iron before you go into the sandstone. The implication being that where there's iron in the sediment, there's no evidence for wave interaction with the sediment. It's massive. It's chemical sedimentary rock, there's just no wave interaction. It's below wave base when you see iron in the sediment. That is an important implication because wave base sits at the same depth as the photic zone. So if your sediment shows clear evidence for deposition below wave base, that means that sediment is being deposited below the photic zone. The implication here has to do with the iron oxidizing bacteria. The only bacteria that can oxidize iron below the photic zone without sunlight is an iron oxidizing bacteria that needs very low concentrations of free molecular oxygen. So here again, from a hydrodynamic sedimentological point of view, we don't see evidence that that iron plume in the contorted bed ever got into the photic zone. So if there was iron oxidation by bacteria, it most likely happened below the photic zone in dark water, and the only way to efficiently do that is you need very low concentrations of free molecular oxygen. Now, the reason why I'm trying to hammer this in is that I think a lot of people in geology, from their vague remembrances of historical geology, a lot of people have no issue with oxygen in oceans on the early Earth, but just like the oxygen was always being used up. There's no evidence for oxygen in the atmosphere up to about 2.4 billion years ago. But that doesn't mean there wasn't oxygen in the ocean. It could have just consistently been used up. But then you get a certain group of geochemists. They're quite hardcore, you can almost call them geochemical extremists that say, when you see evidence for oxygen in the atmosphere, that's the first time there was free molecular oxygen in any superficial environment on Earth. They essentially say when you see evidence for atmospheric oxygen, that was the first ever emergence of cyanobacteria and oxygenic photosynthesis. I do not agree with that view because I think there's a lot of indirect evidence for free molecular oxygen and its interaction with probable very primitive bacteria well before what we call the Great Oxidation Event. So there, you've got a below wave base issue. That unfortunately also happens sometimes. A lot of people, they're excellent geochemists, but unfortunately lose a bit of appreciation for the sedimentology. And I always say you're building a pyramid and the geology forms the basis, and you can't interpret geochemical data in such a way that it's completely contradictory to the actual geology. So now we go back to the Muzan, to the Pongola. We're still sitting in the Meso-Archean, and here we're going to look at these weird life forms. We were very privileged we published this back in 2017, but more recently this year we got a second publication out in Scientific Reports. This is the Nkonga Formation. This is the oldest known granular iron formation on Earth. Now, what granular iron formations are is they're essentially banded iron formations or massive chemical muds, but what they do is they precipitate in water that still has significant wave agitation. So the chemical sediment gets reworked into little granules or balls, and you get a granular iron formation. This is the oldest one we know of in the geological record. It's about 2.9 billion years old. It's not just that it's very old, that's weird. It's the fact that it just looks very strange. If you look at the right, these are thin sections of the granules in this thing. And if you look at them, they show a bunch of different morphologies, it appears like. For example, if you look at the image that's over here, middle left, and you look at the one that's bottom left, it looks like two granule morphologies. But what's actually happening is you're looking at different sections through a similar granule. And if you look at this perfect cross-section view we get here, it does appear like you have these little domes protruding outside this granule. And they do look like biological structures. Now, we decided this is a good opportunity to play with computed X-ray tomography. X-ray tomography can image things based on density differences. Now, people have in the past tried X-ray tomography on stromatolites and other biological structures. Very often this fails because what you can see with a naked eye might be invisible to the X-rays because the structure in the matrix is a similar composition and a similar density. The X-rays won't delineate it. But in this case, you've got a chert granule that's encrusted with magnetite. So we went to Nexa and we started putting this thing on the on the CT scanner, and we started reconstructing this. So yeah, there's a big sample. The resolution isn't great because the resolution is determined by your sample size and how close you can get it to the X-ray detector. But we very nicely reconstructed this granular iron formation, and we could see the larger scale sedimentary structures in there. You get these beautiful upward fining beds. We could see that these are probably density currents that deposited these granules. And there you can see a transition between a lower bed and an upper bed. There in the middle, you essentially see like a iron-rich mud. But we wanted to see these individual granules. So we zoomed in and we did a much closer scan. Now, here you see some of these constraints you get when you're doing petrography on thin sections. The slice can introduce a very heavy two-dimensional bias. And in our original paper in 2017, we had a lot of kickback from the reviewers saying, but what about this and that and these? He referred to 2 or 3 different granule types. And we kept on saying, no, it's all the same granule. And as you looked at that pass-through, you saw that what looks like little clumps of small granule aggregates are actually all sitting on the rim of one larger granule. So because you're doing X-ray tomography, you can extract one of these individual granules and you can reconstruct it in 3D. That is quite small. That's about 2 to 3 millimeters across. What you're essentially seeing, except for some sedimentary transport damage, is you're looking at little micro stromatolites growing on the surface of a chert granule that was every now and again being moved or agitated in a shallower water environment. There's very strong geochemical evidence that life was around, and it's very difficult to explain these structures in a non-biological way. And as you say, that all that white you see there, it's false color, that's magnetite. So it's likely that you had iron oxidizing bacteria colonizing in little domes around these chert granules about 2.9 billion years ago. And all these granules look the same. That is what they look like. I always say it looks a bit like a river pebble that got acne, or maybe an alien brain. But we were very happy with the study, and we finally got the 3D study published in Scientific Reports this year. And we also were able to put them back into the rock to look at the different granule orientations. And the reviewers we had, they were geomicrobiology experts, and they were very comfortable with us calling these biological structures. Now that's the Meso-Archean, the Wits Pongola, but now we're going to move into the Transvaal Supergroup. And the Transvaal Supergroup really is a treasure trove in South Africa's geological record. It basically sits at the Archean to Paleoproterozoic boundary. It records that transition. It's got a fully conformable transition across the Archean Paleoproterozoic boundary. It has a full conformable sequence that records the great oxidation event. There's so much evidence for life, direct and indirect, in the Transvaal Supergroup. It occurs across a broad region of South Africa, in the Transvaal region, in Botswana, as well as the Griqualand West region. And it contains, of course, world-class mineral deposits as well, especially iron and manganese ores. So now I want to tell a story about 2 groups of living organisms. I'm first going to talk about the stromatolites, and I'm going to call these the beach bums. So they're the beach bums for a very simple reason. They loved living on these stable carbonate platforms, not too much detritus washing in, calm water conditions, bathed in sunlight. They were just living it up, you know. And you can see here, this is one of the best geological outcrops in South Africa. And if you're happy to drive on a dirt road, but it's actually easy to get to, it's right on the border between the Northern Cape and the Northwest Province. This is Boetsap. And if you look there, that's like an old stream section that cut in. And those domes you're looking at are stromatolites, and big ones, like the size of minibus taxis. And you can see there at the back people for scale. So this is a specific facies within what we call the Campbell-Rand subgroup. And these stromatolites grew nice and big. They didn't have to grow steep, probably because the water was quite shallow. And you can see that on the right. You can see these beautiful ripple marks. And you can see the ripple marks go away in direction from the top of the dome to the side, essentially that the water would wash over and then flow down and to the sides of these stromatolites. It's absolutely amazing how well the paleo environment, which this is about 2.55 billion years ago, how well it's preserved at Butsap. And the stromatolites, these beach bums, of course, you can use their morphology to infer water depth. When the water got deeper and sunlight became less, they would sometimes go from more domal shapes to columnar shapes. They would grow smaller, they would grow steeper to get to the sunlight more aggressively. And if you look there at the bottom left and the bottom right, these are other morphological examples from the same Campbell Range subgroup. And also interesting, what did stromatolites do to pass the time? They passed the time by passing gas. That's mostly what they did. And you can see this fossilized as well. So there on the left and on the right, you can essentially see what's called fenestrates, fossilized gas escape structures. At times, this gas would even escape through probably what was unconsolidated mud, breaking up the layering as it goes. So a lot of gas was coming off these bacterial colonies, feeding into the overlying water column. And of course, great about these carbonates, they at least have the common decency to leave behind some fossils. So in some of the cherty layers you get in there, they have found very convincing microfossil structures. Even way back in 1987, this was already being discovered and published. But now we go over to the iron and manganese formations, my favorites. I call these the creatures from the deep. So here you get the Kuruman iron formation on the left and the Hadean manganese formations on the right. They really lived in deeper water, darker water, dirty water, water that was very, the environment had a lot of dissolved iron and manganese around. Deeper levels, you don't see a lot of wave interaction with it. It's highly variable. So these things really loved a very different paleo environment to the stromatolites. So these beach bums and the creatures from the deep were always fighting for survival. And there's a beautiful transition at Kuruman Hill in the Northern Cape Province in the Griqualand West region. It's about 5-6 kilometers outside the town of Kuruman. And if you walk up the hill, you're essentially walking up the top of the Campbell Range subgroup. You see the stromatolites changing shape. And at some point, the stromatolites disappear. You start seeing manganese nodules in the carbonates. You go into this shale. So the water is getting deeper and it started drowning out the stromatoforms. They could no longer survive. The water got too deep, it got too dark, and it probably got poisoned by iron and manganese coming in as the sea level was going up. And then you go into iron formation. That's the base of the Kuruman iron formation at the top. Not just that, that shale you see there, that marks the boundary between the Archean and the Paleoproterozoic. So you can do a beautiful walk up that hill and go from the Archean into the Paleoproterozoic. And at the top, when the water's at its deepest, that's where the iron oxidizing bacteria started to flourish. That's at a fairly broad scale. But if you go to another region closer to Kuchas, you're in the Kuchas subgroup, and you can look at the Rooinacke iron formation. This is a farm very close to Griqua town, and there in one single outcrop, you can see a backflip transition between these two paleo environments, where you can see the iron formation, a stromatolite, back into iron formation. Even the top there, you can see interlayering between carbonate and iron until you're essentially drowning out that stromatoform, and you go back into deeper water iron oxidative style environment. So even there, you could see different organisms fighting for different ecological niches. Now, here we talk about the Great Oxidation Event, 2.4 billion years ago approximately. Things have never been the same again since then. And there's a very well-known plot if you go to geochemistry conferences and you sit in any early Earth surface environment session. This will pop up 2 or 3 times in different talks. There you see mass-independent sulfur fractionation. On the right, prior to 2.4 billion years, when you look at sulfides, you measure their sulfur isotopes, there's mass-independent sulfur fractionation. How do you do that? Well, UV radiation. There's no ozone layer, so all the sulfur being deposited undergoes this mass-independent fractionation. But at 2.4 billion years, that disappears, and it just doesn't reappear in the geological record. So the best interpretation for that is that was the first evidence for an ozone layer, and you need a certain minimum oxygen level in the atmosphere, which I think is about 1 to 10% of present atmospheric levels. Then you form an ozone layer. So essentially, there we go. That's the great oxidation event, very clear cut. There you start getting manganese deposition on steroids. So some of your biggest manganese deposits form from 2.4 to 2.2 billion years ago. And essentially, you start the banded iron formation extinction. There you see through time how common banded iron formations are in the worldwide geological record. And 1.9 billion years ago, they basically disappeared. So when the great oxidation event happened, you're essentially making environments more and more oxidizing, meaning you can't transport iron from source to sink very far. So iron stays close to these vents, which are probably sitting on oceanic crust and getting subducted and recycled. So your passive marine margins started getting starved of iron and eventually manganese input. And of course, for me, that's a very sad time in Earth's history. # never forget the extinction of banded iron formations. Now, this is followed by what people call the boring billion. But a lot of other people, from about 1.9 billion years ago to about 900 million years ago, a lot of geochemists call it the boring billion with regards to paleo environments. Please note, lots of interesting igneous and continental, tectonic stuff happening. But from paleo-environmental point of view, the oxygen levels overshot, but then went drastically down again. So you've got oxygen around, but it's just sort of at a critical level that life's evolutionary development is stunted. But then we get to the Neoproterozoic from around 800 million years ago, and things start getting interesting. And that is around where we get the snowball Earth event, where you see evidence that basically most of the Earth was covered in ice, where you have got clear evidence for glacial deposition happening basically at the Earth's equator through paleomagnetic studies. And here in Namibia, this is a picture from close to Kurigas in the Gulb Formation, which is about 630 million years old. And there you see beautiful, these what we call these snowball Earth sequences, where you see a glacial deposit transitioning into a cap carbonate, and the bottom of that cap carbonate is quite full of manganese. So you remove the ice, you put oxygen back into the water column, and all the manganese drops out. But it's not just manganese dropping out. There's other interesting things happening as well. Like, for example, just following there were two big snowball Earth events, the Sturtian and the Marinoan. We talk about it's called the, sorry, I can't remember now the broader term, but you get the Sturtian and Marinoan snowball Earth events. After the last one, you get the first very nice fossils for complex organisms, and these are called the Ediacaran fauna, very nicely preserved in Australia as well as Canada, and where you start seeing sponge-like creatures, worms, very interesting marine creatures coming, and this predates the Cambrian explosion of life. But banded iron formations made a comeback, baby. Yes. So there we go. They sit in the glacial deposits, because if you have a snowball Earth, you're capping an entire marine basin with ice. You're cutting it off from the atmosphere. So very quickly, that water will become reduced, completely reduced. So it will start dissolving iron and manganese into the water column. What happens when you melt the ice? You put oxygen back in the water, and you dump out all the iron in a little iron formation that sits interbedded with the diamictites. And for me, this Neoproterozoic, these Neoproterozoic iron formations gives me as much joy as the Yoda cameo in Star Wars The Last Jedi, the return of a true legend. So, these rocks are fantastic. But what about South Africa? So the stuff there I spoke about was the stuff up in Namibia, which sits in the Damara belt. But in South Africa, we also get the Nama and Port Nolloth groups. They very nicely record the snowball Earth events, just not as well exposed and always as well preserved as the examples in Namibia. And here's a beautiful outcrop. It sits close to Fjolsdrift, the border post. And this sits just in South Africa. It's right on the Orange River. It's a carbonate outcrop, and you very easily walk over it and you miss it. But then you start looking closer at this outcrop. And this is sitting in the Nama group, if I've got it correctly. And now if you look closely there at the ruler and you look very closely and you zoom in, there we go. There you see Ediacaran fauna, just smaller, like the poor man's Ediacaran fauna. And that thing right over there is called Claudina, and that's what it looks like in 3 dimensions. It's a little worm-like creature that lived in shallow marine environments. Now, of course, that's not sort of the end of my story with regards to this early life. And of course, in South Africa, if you go younger, you get beautiful Triassic and Jurassic fossil successions. We've got the Cradle of Humankind. So I focused on the old stuff and the dubious stuff. Nice thing about dubious stuff is you can debate it, and which can sometimes lead to more publications, although each publication comes with a lot of blood, sweat, and tears. But I mean, for people working on younger stuff and eukaryotic fossils, South Africa still has a lot to offer. So essentially, now I'm concluding. So South Africa's geology is a treasure trove for early Earth studies. We have beautiful chemical sedimentary successions, and there's still a lot of potential for geochemical studies, especially non-traditional isotopes, non-conventional dating techniques, especially on free oxygen. You know, people are fighting about that, how clear the evidence for free molecular oxygen prior to the great oxidation event, how clear that evidence actually is. So there's a lot more work and refinement that can go into that. Now, in South Africa, we know the geology pretty well, but we want to know more. And especially for international collaboration, this is great because we know where to take people. We know how to find the samples. We know how to give the geological context. But in South Africa, you know, it's getting better, but quite often our geochemical abilities can be quite limited. So join the dark side of early Earth studies. And that is my talk. Thank you very much. So I'll hand it back over to Grant.
Bertus, thank you so much. Keep your screen share up there, just in case anyone has any questions. Thank you for that very entertaining and informative talk, and your passion for BIF is infectious, and we appreciate it. Okay, so I'm sure you'll be willing to take some questions now, Bertus. I'm just going to explain because the audience members may not be familiar with how to ask questions on Zoom webinar. So there's 2 ways of doing it. On the bottom of your screen, there is a raise hand icon. You can click on raise hand, and I see Sue's already done that. If you want to ask a question, raise your hand and I'll unmute you from this side. Or you can also ask a written question in the Q&A and I'll pose that to Bertus. So you have 2 options. And of course, if you're watching on Facebook, there are about a dozen people watching on Facebook. You can also ask a comment in the comment section of the video and I'll pose that to Bertus as well. So Sue, let's go to you first. I'm giving you the microphone. And you just need to unmute, Sue.
Hi, can you hear us?
Yes.
Yes.
Okay, I'm sorry, Bertus, but the question is from Lou, not Sue.
No worries, Lou, go for it.
Okay, baby.
Yeah.
My question is about fossil bacteriums, individual ones. And, you know, I've been aware of people writing papers about these things in charts since the 80s.
Yes.
And more in Archean charts. And more recently, there was this irresponsible NASA debacle where they claimed to find a bacterium in a meteorite, proving that there was life on Mars. And then even more recently, there was my dear friend Martin de Witt and his friend in Norway, whose name is, I forgot. That doesn't matter. Where they were claiming to find individual bacteriums in pillow glasses from Barberton in the Archean. So, you know, I've always been very skeptical about these structures. I wouldn't know a fossil bacterium if it bit me in the leg, but my question is, and I think you answered it actually, my question is, do you see clear-cut bacterium fossils in young cherts, like the ones that are forming right now? I mean, the Earth environment today should be teeming with bacteriums, and maybe even get a COVID-19 fossil someday. So,
Lou, that is actually a very good question. Now, most cherts we get on Earth today are biochemical cherts formed by radiolarian diatoms. So you see the radiolarian diatoms in there, beautifully preserved. So of course the problem with that is a niche environment dominated by radiolarian diatoms. So in that case, no, you won't see fossilized bacteria in those cherts because it's flooded with other organisms using the silica in the ocean. However, when it comes theoretically, if people claim you can get fossilized bacteria in volcanic glasses, surely then that should also happen in modern environments. However, to be honest, Lou, it's not really my area of specialization, so I don't actually know. I have a guy I can email to ask that question, but I'll probably only be able to give you an exact answer in a couple of days, because he's one of those people that'll sample 50 samples of cherts, you'll make 100 thin sections, and you'll just go from thin section to thin section hoping to see something. So I'm sure you would be able to tell me how recently you see these sorts of fossils. But Lou, you're absolutely right. And I mean, some people have claimed fossilized bacteria in Archean rocks from Australia, but then quite convincingly, other researchers showed that inorganic hydrothermal veins can form these same structures. So, and in that case, the researchers messed up because they sampled close to those veins. Whereas there's a lot of other examples where there's no hydrothermalism in the environment. It's really pristine samples, especially in these late Archean Paleoproterozoic carbonate successions. I think those fossilized bacteria examples are much more convincing. But these things that come from old sequences where there's been a lot of time for hydrothermal interaction, veining, I agree, Lou, those get very, very dubious. And from a moon rock or a Martian meteorite, yeah, I don't know. I would also be very skeptical when I read that. So Lou, we need those skeptics to weed out the junk.
So are you saying that there are no modern day or reasonably young cherts that are formed by the same processes that you get cherts in the Archean?
Well, as I said, in these volcanic glasses, it should be the case, I would guess, because volcanically active environments on Earth are teeming with bacterial activity. It's just most of our cherts, your standard marine cherts today, essentially are the dead bodies of radiolarian diatoms. Whereas cherts back in the Archean, they were precipitating in a very different fashion because radiolarian diatoms weren't around. So for marine cherts, I wouldn't expect that. But theoretically, these cherts that you see in hyaloclastites in volcanic glass, I would think if they were doing this back in the Archean, they should still be doing it today. But I would have to ask someone who actively works on this to give you a definite answer.
Okay.
Thank you.
Thanks, Lou.
Any other questions? There's a little bit of time for questions. I'm not sure if Bertus is going anywhere, but if you have any questions, just simply click on the raise hand button. And I think I see a question from George Henry. So George, I'm allowing you to ask your question and you'll need to unmute.
Thank you, Grant. Bertus, a very nice talk, much appreciated. Bertus, you and I went on the field trip to Namibia together with the UJ Geology Department a couple of years ago.
Yes.
And I did a lot of work there. And one of the, of course, the enigmatic things that I found during my field work donkeys years ago were the iron formations associated with the diamictites. And we saw some of those sections. Now, the question is, the picture you showed was from somewhere else in Namibia, where you had diamictites.
Further north, yeah, from the Chouos Formation.
Yeah, the Church formation, exactly. And then you have the iron formation, and then you have diamictite. But how would you explain the situation that I saw where you actually have got the diamictite and you have an iron formation and you had drop stones in the iron formation, and then again you have more diamictite. So it was a bit puzzling as to how the drop stones were actually being deposited, or the lone stones, in the iron formation as they were forming. So the environment is the what I'm trying to get at. You're depositing diamictite and then iron formation together with these lone stones and then diamictite.
Yeah.
So it's the interbedding and the lone stones that could explain.
Yes. Okay. So George, it's a glacier marine depositional environment, which is its entire own beast. I'm not a glacial expert, but I mean, there's some very nice couple of papers that a student from McGill University in Canada, Max Licht, he's Australian, but he studied in Canada, where he has published some nice papers on the sedimentology. So essentially, if you actually look at the diamictite, you don't go diamictite BIF like sharply. The diamictite leading up to the BIF and following the BIF is actually ferruginous diamictite. So what's essentially happening is there's still ice around when you're opening the water column back up to oxygen. So there will still be some ice flows around and some melting ice dropping these drop stones into the iron-rich sediment. Because there's a transitional period. So it's not just like you remove all the ice and then the oxygen comes back in. As you remove the ice, the oxygen in some part of that water body will start slipping in. So you will see some parallel diamictite and iron deposition essentially happening. So I think that could easily be explained probably by floating ice coming into the glacial marine environment because there's a lot of waxing and waning of the ice. Glacial, interglacial, although not really interglacial. So it's actually these glacial marine depositional environments are very complex and show a lot of cyclical changes. So that is how I think I would explain it, but I can find you that paper and send that to you if you want to read the researchers from McGill, their detailed explanation of it.
Thank you, Bertus.
Thank you, George. Any other questions? Simply click on the raise hand button at the bottom of your screen. Okay, Bertus, I've got a very quick question.
Go for it, Grant.
Not thinking about questions. What reason do you think, or what is your understanding of the boring billion and why it was so boring from a paleo-environmental perspective? What caused that?
It's sure, there's a lot of hypotheses on that. Unfortunately, a lot of them didn't stick in my head. But essentially, if you look at a lot of the geochemical proxies in marine successions, it looks like the oxygen content in the atmosphere had almost an overshoot, where from 2.4 to about 2.2 billion years ago, it jumped up to above 10% of present atmospheric level. But then something happened again that at about 2.2 to 2 billion years ago, those levels went back down to about 1%, and it stayed there for a billion years. So I'm not sure exactly what could have caused that, but essentially it's like a mini ecological disaster. So the rise in oxygen caused an ecological disaster because a lot of life on Earth, free oxygen was poison. But then at the same time, these loads of oxygen open it up for other organisms to flourish. But then they could flourish for about 200 million years, and then suddenly it dropped back down again, meaning for about, it stagnated evolution on Earth or put it at very low levels, just enough for eukaryotes to evolve for a billion years. Now that overshoot and that drop down, I've heard some hypotheses. I think one is like, I think quite often these things are caused by large igneous provinces, to be honest. I mean, things like, the Deccan traps and the Siberian traps. I mean, you don't put that much lava onto the surface of the Earth without significantly poisoning whatever life is trying to do. So it's probably that, because these big igneous events introduces certain sinks into your marine environments. So that means suddenly when you get this overshoot in a certain chemical compound, these large igneous events can just draw it back down again. And quite interesting, this is still highly debated, but when you go to the Francevilian in Gabon, you see very weird structures in the rock that look very Ediacaran-like, but the Francevilian is 2.2 billion years old. So there's also a hypothesis that you had a failed Ediacaran-style evolutionary event at 2.2 billion years because of this overshoot of oxygen that just got drawn back down again. But people are debating it. But I've seen the rocks, and I've not been to the field there myself to check the successions. But if you look at it, it looks like typical Francevilian shales, and it contains structures and features that look a lot like Ediacaran-style fauna in a rock that's 2.2 billion years old. So I don't know. I think that's still under a lot of scrutiny. But what people don't debate is you had this temporary overshoot of oxygen levels that drop back down. And I would say that initial kick up was probably brought back down by a large igneous event. That to me would explain it the best. However, if you want to ask me what large igneous event, because I've not actively researched it, I don't actually know.
Okay, thanks, Bertus. We've got one last question, if you don't mind, from Glenn, who's unmuted and she can speak up.
Go for it.
Thanks, Bertus, for a very wonderful talk. I only have one question. On the lower part town formation, we have this light brownish dull orange unit of ferruginous carbonate, which tend to mainly occur at the intersection between carbonaceous mudstone and magnetic mudstone. What led to such formation? I mean, what sort of processes were actually in play there? And
that carbonate, is that an anchorite, siderite-rich carbonate?
Yes.
Is it iron-rich? It's an iron formation. It's just a carbonate facies. I think you're talking about the water tower iron formation.
That's correct.
Yes. So the water tower iron formation is a weird one because it's not like the contorted bed is laterally continuous. It looks the same across hundreds of kilometers. Whereas the water tower iron formation, in some places it has a BIF, but like at Walter Sisulu, it's just a magnetic shale. The BIF never fully develops. So quite complicated lateral depositional environment. Now, how you explain that is very simple. That would probably be slightly shallower water. There would be a lot of organic carbon going into the sediment with the oxidized iron. So essentially, if you put ferric iron and organic carbon into a sediment, the two will immediately react. The iron 3+ will act as an oxidant. The organic carbon will act as a reductant. What do you form? You form ferrous, Fe2+ iron, and you form carbon dioxide. And during diagenesis, they just beautifully combine to form a siderite or an anchorite. Even if you go to the contorted bed, internally it's very mineralogically complicated, and it varies between oxide and carbonate facies. What just very often happens when you see an iron formation at surface, quite often very recent African land surface related weathering has turned all the carbonates into hematite. But yeah, that's essentially how I explain it. You explain it that you put enough organic carbon in the sediment with your ferric oxide hydroxides that essentially during diagenesis, all of that gets turned into iron-rich carbonate. And it's very common in many iron formations. You see that carbonate facies. It's very common. You see it in the Kuruman. You see it the other iron formations in the Wits and Pongola. So it's a very common process that happens.
All right. Thank you, Bertus. And thank you again for that great question. So before we end off, just to advertise the next Geotalk. It's not going to occur next week because next week is Heritage Day on the 26th. So Geotalks will take a break. But on the 1st of October, we'll have a very interesting talk from Jim Mangal and Sam Robb from Carleton University in Canada on emplacement mechanisms and cooling history of the Rustenburg layered suite, some new perspectives. And I can give you a heads up that talk is likely to elicit some very interesting debate. So please join us for that. And of course, you are welcome to stay online because we have a little bit of networking that we can enjoy now if you wish. So if you want to stay around and chat with Bertus or anyone else, then just stay online. And thank you otherwise for watching. And thank you to CCIC Group for sponsoring these talks. And we'll see you all on the 1st of October.
Oh, and Grant, just quickly, I want to say thank you to everybody who attended the talk, and thank you for all the questions. These were really great questions. I really appreciate that. Thanks, everyone.
All right, thank you, Bertus. Much appreciated.